Hi, my name is Dominic Bleacher. I'm a freshman mechanical engineer here at Ohio Northern University, and I am the founder and president of the Ohio Northern Rocketry program.
This is the first year of the Rocketry program at Ohio Northern University, and we are excited to continue expanding our aerospace program. We are a smaller college based in Ada, Ohio, known for our emphasis on quality education in all professions, especially engineering and pharmacy. We spent the start of the season teaching new members design, simulation, and build skills with our Level 1 High Power Certification program. This served as a stepping stone into two-stage high-power rocketry and allowed new members to learn quickly through hands-on experience. In addition to the Level 1 program, we have a few members who have worked towards obtaining their ham radio technician's license for avionics and other experimentation purposes. Now let's move on to our 2025 Argonia Cup competition build.
I'm Aaron. I'm a junior mechanical engineering student, and I'm the vice president of the ONU Rocketry program, as well as the media lead for the team. We started the design process by analyzing the scoring equation. To do this, we created a contour plot as well as a 3D surface plot in Python to model the number of golf balls and the total altitude across different ranges. We also made a scoring calculator with 3 sliders for the different parameters in the scoring equation to easily calculate the points scored for a specific set of conditions.
After figuring out the optimal parameters for this year's scoring equation, we created an open rocket model which served as the basis for all CAD and fabrication of the rocket. We ran numerous simulations in OpenRocket to ensure that all avionics, including redundancies, would meet competition requirements for deployment speed and timing. After simulating various motor profiles, we determined that an L1000 and a K270 from Aerotech would be optimal for this year's competition. We decided that a 3-inch diameter airframe would be optimal for this year's competition since it is not as difficult to fabricate as a minimum diameter build, and it also allows us to do a through-wall fins for increased strength. For motor retention, we used Aeropack RA54P threaded retainers.
Hello, my name is Jacob Rust. I'm a senior mechanical engineering student here at Ohio Northern University. My role for the rocketry team this year was putting together the full CAD model for our competition rocket and then also helping with some of the sizing in the booster. So the main goal for the booster this year was to minimize the weight, and to do that we opted to use a 40-inch body tube, as you can see here. And unfortunately, using that smaller body tube only gave us about 10 inches to work with after we put in our motor tube. So this causes some problems with recovery. We want to make sure we have enough space for our recovery itself and enough space for the separation charges to build up pressure to have good separation. So in order to space everything correctly and size them, we've needed to take what we estimated to be 10 inches of packed length of our parachute and make it smaller. So after trying some different ways of wrapping it and packing it down, we reduced it from 10 inches to 6 inches, so it gave us 4 inches back in the body tube. So now we had about 14 inches to work with for the sizing of the charge wells and the amount of black powder we needed, and then also to the avionics. Now that we determined we have 14 inches of length left in the body tube of the booster, we could then start sizing our coupler, our switch bands, and also the space needed to build up some pressure for separation. Really what drove the remainder of the design for the booster came from a couple different restrictions. The first being that we needed to have 10 psi in order to separate using the separation charges, and then also too, we needed to have the coupler between the booster and the sustainer at least be recessed 3 inches. Under those constraints, we then followed an iterative process of changing the amount of black powder we needed and the volumes that could build up pressure, and then the sizings of our couplers and switch bands. So what we landed on was a 10-inch coupler and a 4-inch switch band. The reason why we chose a 4-inch switch band versus a 1-inch like the sustainer is because if we used a 1-inch switch band, we'd have little to almost no room for the booster avionics.
The airframes were commercial G12 fiberglass airframes which were cut to length according to the OpenRocket simulation. Both the sustainer and booster fins were a custom profile. The fin profiles were recreated in CAD, 3D printed out of ABS, and then traced onto G10 fiberglass and cut out. The leading and trailing edges of the fins were then chamfered using a belt sander.
Hello, My name is Ryan. I'm a freshman mechanical engineer at ONU, and I was part of the construction team for this year's build.
For the booster, we first started by epoxying the centering rings for the motor tube. We epoxied first the forward ring and the mid ring, and then epoxied in the shock cord. After we epoxied the rings on the motor tube, we then put epoxy inside of the booster tube itself, lowered the shock cord through the tube, trying to avoid touching the epoxy inside. And then we slid through the motor tube with centering rings. We then moved on to the fin tabs by setting them in with epoxy. Then we took some very runny epoxy and let it just run down the side of the inside of the tube, as well as the fillets on the outside. And we repeated that each time. 6 on the outside, 6 on the inside. Once all of those fins were in, we epoxied in the aftering, and that was pretty much the booster. The sustainer was basically the exact same as the booster. However, instead of epoxying the aftering after putting in the fins, we epoxied the aftering with the other centering rings and put it into the sustainer tube. And then when we tacked in the sustainer fins, we used a syringe to inject epoxy and let it run down the inside of the tube for the interior fillets. And then we did the same process as the booster fillets for the outside, and that was the construction of the sustainer.
The nose cone is a commercially available 5:1 ogive fiberglass nose cone with an aluminum tip.
For our payload, we're fitting 10 golf balls in the nose cone of our rocket. To keep them inside, we have a insert for the nose cone. We have 6 weld nuts that will have a bulk plate bolted on to keep the golf balls inside the payload or the nose cone section and prevent them from spilling out into the rest of the rocket.
For recovery, we chose a 36-inch booster parachute, 24-inch drogue parachute, and a 58-inch main parachute. And yes, it's a bright neon pink because why not? We used 3/8-inch by 30-foot Kevlar shock cord with sewn loops for swivels. The descent rate of the main and booster parachutes was calculated to be between 28 and 30 feet per second.
I'm Parker West. I'm a computer engineer here at ONU, and I am the main avionics lead. So for this year, we will be using 2 different types of brands of computers. We will be using a Silkdyne Fluctus and an Altus Metrum Telemega. For our sustainer, the Fluctus is going to serve as our primary with the Telemega as a backup. And also for a booster, we're going to have a Fluctus as a primary and a Telemega as a backup.
For our booster logic, it's relatively short. So when the Fluctus detects the burnout of the booster motor, it will fire Pyro Output 3, which is our separation charge. This will also be set to a 2-second delay, so the booster will coast for a total of 4.7 seconds. Then, when it detects apogee, it is going to fire the main parachute for the booster. The Telemega is relatively simple. All this has is an apogee delay, so when the booster reaches apogee, it will fire the main parachute 2 seconds after that, which will account for enough time in case a computer fails. Standard logic, the first thing the Fluctus will do is it will sense when the booster motor is burnt out, indicated by wind burnout. And so when that happens, it will set a timer for 6 seconds. Then our next event is going to be at any time during the flight, all of these conditions right here must be met. So the timer must reach greater than 6 seconds, which is approximately enough time for the sustainer to drift away from the booster. And the vertical angle must be less than 20 degrees. And the speed in meters per second must be greater than 61, which is approximately 200 feet per second. These latter 2 restrictions are set in place at us by Argonia, so these must be met for the sustainer booster to fire. So then, if all these conditions are met, they will fire Pyro Output 3, which is our booster motor. Then, when the rocket reaches apogee, it will fire Pyro Output 2, which is our drogue parachute. Then, during descent, when the altitude is less than 250 meters or 700 feet, it will fire Pyro Output 1, which is the main parachute. Some notes to add for this too, this one-shot button ensures that this block of code will only execute once. And also to note that this Fluctus is station alpha computer. There's going to be a main deployed altitude, which the Telemago will automatically detect when the rocket reaches the main deploy altitude, so our main shoot. So this altitude is going to fire around 600 feet, which is 100 less than our primary computer at 700. The apogee delay will be set to 2 seconds, so when it reaches the apogee of flight, it will wait 2 seconds before firing the drogue parachute. Then, to configure the pyro channels, which takes a really long time to scroll through, we will have, so the ascent rate must be greater than 200 feet per second, which note all OS will round this down to 199.9, but it's still 200 feet per second. And so the vertical angle must be less than 20 degrees. And then it will fire after motor number 1, which will, the Telemago will automatically detect when a burnout of the booster motor has been fired, so that's what that means. And then it will delay 7 seconds after all these conditions, so that will ensure that it has some coasting times.
Thanks for watching our 2025 Argonia Cup submission video. I am extremely proud of the work this team has accomplished this season, and am thankful for the amazing opportunities Ohio Northern has given us this year. I look forward to this year's competition. Go Bears!